Give it like 3 seconds. I think we're live. It's live, but it's...
On your YouTube channel?
Yeah, hey. Yeah, we are. GM. Let me make it public. Visibility public. Done. Save.
Video
Okay,
unavailable.
now let me get this. Yeah, no, it's another link. Like I deleted the...
Oh, okay. Okay.
Yeah.
Need to retweet it as well so I can get out there.
Yep. Excellent connection. Okay, edit. Philogy's balls. Okay. Such a good meme.
It's the best name. Bytecode assembler with low-level scheduling. Let's go.
Why is this not? Oh yeah, here we go. Okay, I got the link. Wait, let me tweet it out. We are live. We're looking at Philogy's balls. Let's go. Okay. Okay, should we wait for one comment?
Yeah. Let's give it time to
GM. Yeah.
go through. Just searching for. All right. Let me also retweet. Okay. Should I also open the comment section on my other monitor? Then I can also follow.
Sounds good.
Is it on your YouTube channel or the bytecode YouTube channel? Oh no, it's your YouTube channel.
Oh,
Okay.
I don't have. It's like one. It's only my.
Ah,
yeah,
okay.
Yeah. Very professional here. Okay. Damn, we're professional streamers now, Philogy. Nice art.
The comments aren't loading for me for some reason.
The comments aren't working for you?
Yeah, they're not working for me. I mean, are there any?
Oh, that's weird. I posted something. Let me post GM again.
Okay, it's fine. You'll just have to relay to me what people are saying.
Yeah, for sure. I will keep an eye on the comments.
All right. Hi everyone. I mean, the people that are here. I guess we can do a little intro. Yeah, so I'm known as philogy on Twitter. I post about low-level smart contract development stuff and security stuff. And yeah, I'm currently here live from New York at the Sorella offices / house. And yeah, here with Shafu. You want to present yourself as well?
Nice. Yeah. GM guys. Yeah, this is the bytecode where we look at interesting stuff, I guess. And I started looking at Philogy's balls. I don't know. It's a very good name. But what BALD stands for is a bytecode assembler with low-level scheduling, but it's most famous for being philogy's balls, I guess. Yeah, so I started to look at I, st- I started to look at philogy's implementation, and I thought to myself, man, it would be awesome to have one to do a code walkthrough how to use it, why he implemented it in the first place. So that's what we are doing here. So this is yeah, we're streaming this live. This is the first ever live streamed the bytecode episode. So if you guys have any questions, put them in the comments down below. Awesome.
All right.
Philogy, should we start by let's introduce what Balls is exactly.
Yeah, so Balls is like a new language slash tool to generate Huff code. So the idea is that it assists you in writing low-level code. And yeah, the reason you want to do this is one, writing low-level code is fun, but it's also really tedious and annoying. And the most time-consuming part of that is stack scheduling. So it's the idea of organizing your variables and values into the stack in a specific ordering and making sure that's maintained everywhere. And yeah, it takes up a lot of time, and also it's often hard to get the optimal layout, especially manually, because you have to try different combinations, you have to see if it works, and especially in Huff, where you're maintaining like stack comments to make sure things look nice, like for example these stack comments here, it can be quite time consuming. So Balls basically lets you write almost Yule-like code, and then it'll just auto-generate for you the resulting Huff code. And also based on the options you give the compiler, it'll also optimize, and even in certain cases can guarantee you the optimal stack layout for your macro, which is really great. Like if you compare the code here and here, like here it even has comments, so it looks like it's a similar size, but it's much more readable. Like you can see, okay, I have a variable here as input, I'm loading some stuff from call data, I'm doing some stuff with it, and then I call return at the end, and then you get this Huff code, which without comments is not very readable, and things are also in like a weird order, right? Like up here we defined it that the two call data loads are right next to each other, but if you look in the resulting code, actually they're not next to each other, because I guess it discovered here that this is one of the orientations that lets you save instructions. So the main thing it's trying to optimize for is swaps, right? Because everything else is kind of necessary, like a dupe. You need that when you're referencing a variable, right, multiple times, like for example this too, or wait, like for example this from balance, when you're accessing it multiple times, so here and here, you need to dupe it, right? There's no way around that. Or the call data load itself, you can't avoid that, right? But things that you can avoid are swaps, right? Especially here in this code where it only works for continuous code. That's another limitation. That's the main thing to optimize for, right? So that's how it's laid out. So I think I would just go into an example and start coding with it. Yeah, definitely.
Yeah, one question. Like when you say optimal in respect of what? Like code size, gas wise, what are we trying to optimize here?
So in this case, it's both gas and code size, because it optimizes for a very specific thing, which is, as mentioned, like the stack layout. And here it's specifically minimizing the amount of swap instructions, right? Because it assumes, so it doesn't have, unlike Solidity or Viper, it doesn't have like a so-called peephole optimizer. So for example, if you're doing something suboptimal, like you're doing multiplication instead of a bitwise shift or something like that, it won't be able to optimize that part for you. Like Balls expects you to already do those kind of optimizations yourself, although it may do that one day in the future for you. But the main thing it really focuses on right now is minimizing the swap instructions, right? So if you look here in the code, for everything, it only used one swap. And if you try to write this Huff code yourself, you may notice that you might end up writing more swaps, just because, yeah, it takes some time to manually figure out what you need to do. And basically Balls just like looks through all the possibilities for you, and then gives you the first one it finds that seems to have the minimal amount of swaps. So that's what it's optimizing for specifically. So it's not necessarily optimal in respects to other things, right? Because it doesn't know how to optimize them yet. But specifically this, which is if you write a lot of Huff code, this is like a big part of it, or like a very tedious part of it is like, yeah, it's writing all this and also maintaining the stack comments. And then the next thing is that as soon as you want to change something, it's very likely to change the optimal stack scheduling, and then redoing all that is again super tedious. So this is a cool tool to write Huff with.
Nice, nice, very cool. Okay, so what should we what do you think would be a great idea to do next? Like look how to use it or jump into the implementation?
I would jump into how to use it and maybe write some code with it. Let's think. What would be something cool to write in low-level code that would typically take quite long, but with balls we can do it quite quickly. I don't know. I'm currently working on rewriting meth with it. So I could show some of that, but that's already done. I feel like it might be funner to write a little challenge. So why don't we go to Gaslight, or how's it called again? The repo from Thomas. How was the? Do you remember how the Gaslight repo was called, where they had all the different snippets, optimized snippets, in there?
No, let me try to find it.
I'm just thinking of something to optimize.
Okay.
Gaslight. Gaslight. Maybe it's pop punk GitHub.
Yeah, I found it, I think. Should I send it to you on Telegram?
You can also send it on Riverside. Oh no, can you send messages here? Oh no, then just send it to me on Telegram, yeah. There we go.
Okay.
Pump Punk
I think I
LLC,
can
Gaslight Core. All right, let's open this up. All right, so I already did in Huff a very optimized airdrop contract, but I think that could be a good one to do, because it seems like it has a lot of like things going on the stack. Let's check it out. Let's check it out. Okay, so here, some assembly, relatively simple loop. I think this might be a good point to start just for now. So let's write a very optimized, an even more optimized implementation of the airdrop contract, right? So let me begin by just initializing a new repo. So let's do we're going to call it just like airdrop balls. And although balls is its own language, like you still need to use Huff, because as I mentioned, one limitation is that it doesn't support control flow yet. So you'll need to do a lot of the control flow yourself still in Huff, but it'll still save you a lot of work. So let's start by opening a new file. And yeah, let's call this airdrop airdrop ball. So if we first look at the implementation here, this is great because it gives us reference implementation that we can start to use. Basically, the goal is to take a token address, take a bunch of amounts and the total, and then you first do a transfer from into the contract, because the transfer from is more expensive than a transfer. So you transfer everything at once into the contract, and then the contract can do a bunch of other transfers out here. So for that, we need to form the call data. We need to validate the return value, although here only the success flag of the call is validated, so not the return value, which will break for some tokens, but let's do that too, because it simplifies everything, and it uses less gas to check less things. And then specifically, I think where we will be saving the most gas versus this implementation is this loop right here, right? Because as I showed on Twitter, the Solidity compiler, even when you write inline assembly, it's not very good at stack scheduling. Like if we take this function, and then we throw it into a Solidity contract. So let's do a quick Solidity contract over here and look at some of the instructions that are generated. And we put that in here. It doesn't have any dependencies, I don't think, so we can just compile this. And let me do optimizer runs. Let me just put optimizer runs to the max so we can see what the compiler splits are when it's trying to do its best. And then if we spit it out, and then we disassemble this quickly, we just can directly get the runtime bytecode like this. The only reason I know this command is because I've just done it so often. But yeah, basically the out folder is just where all the artifacts are stored. Then JQ is a thing for just parsing JSON, and then cast is just the tool that comes with Foundry. So if we look at it here, if we look for, yeah, there we go. So here's the set, and if we look at the jumps, okay, so it has here. Let's open the code next to it so we just see. So let's try and find the body of the loop. The body of the loop will basically, actually this should basically, all right, so we have, this is set up there. Then we have some subs and adds. Yeah, the sub and the add. Then we have the jump test. So I think this is the start of the loop. And then this is the first condition. This jump I. This is the second condition. And look, a bunch of pops to check the second condition. And then this jump should go back to the top, I think. I'm pretty sure this is what that is. And we can also, so this is roughly the loop. I'm pretty sure this is roughly the loop. Or is it this? I know, because this is a break. All right, so this is a break. Yeah, this should roughly be it. But you see, there's a lot of pops, and if we look at the swaps that are here all over, there's actually not that many up here, but there is a lot of pops. All right. Anyway, so yeah, you see that we'll be able to avoid a lot of these redundant instructions in our implementation. So let's open it up. So the way you write a contract in balls is you take all of the pieces of continuous code, and then you write them up in individual like functions, and these will generate macros, and then you can stitch them together in Huff. So like this, you do the least amount of work possible yourself, and leave the balls compiler to do most of it for you. So for example, this start right here, like setting it up and calling the token, we're going to make that into a function. And these little reverts, actually, so that we can revert or check things in our contract, we will pretend in Huff that we already have a Huff macro. So the way you do this is through an external state.
Philogy, could you maybe explain that step again? You split it up into functions, and then that part, if you could go through over that again.
Yeah, exactly. So imagine you were writing this code from scratch, right? So you have these different pieces in the function body. And one limitation I explained is that balls doesn't support any branching code, right? So any function you define in balls, so if I define a new function now, called like my function or something, doesn't have to be all caps, by the way, that's just my convention. If I write some code in here, it can't branch. It's like it doesn't, there's no concept of ifs, there's no jumps, there's no for loops, right? So you have to mix it with Huff to do that. So to be able to write most of our code in balls, so we have to interact with Huff the least, we look at all the continuous sections. So if we look at this code, we would see, okay, all this code doesn't have any branching, right? Here, there's an if, means there's a branch. So this wouldn't be part of it, but yeah, all of this, and even the condition itself can all be in our function. And then as soon as it comes to the if, that will have to like do in Huff. And then similarly here, calculating all this stuff before the loop starts, this can all be one function. But again, as soon as we reach some control flow, like here, for, we have to write that in Huff, so we cannot express that in balls. And then here, for example, the loop body, ignoring these ifs for now, like this is all one continuous piece of code, so we can do that all in one function, right? So for example, here I'll define like transfer body for my for the body of the loop, right? And so one little trick you can do to kind of get control flow, but not really, is like, for example, these ifs that just revert, like up here, and up here. Like you'll have to actually implement them in Huff, but you can basically tell balls that, hey, I'm gonna have a Huff macro called like require or something. That's or or let's do require not, so that if it takes like an error, like if this is 1, then it'll revert. So require not, that'll take no parameters or no inline parameters, and it'll take from the stack one parameter, which is like the flag, like whether it's should revert or not should revert, and it'll return nothing, right? So in the success case, it'll just keep going and consume your value. And also we'll define that it writes a dependency called control flow. So this piece is something special with balls, and is a bit it goes a bit into the weeds, but essentially one way that balls is able to optimize your code is that it like will reorder and rearrange things based on whether on how it's allowed to read them or not. But the danger with rearranging things is that you may actually break the code, because certain things, like for example storage accesses or writing to memory, they have to maintain the order. So balls is aware of dependencies, and you can even define your own that tell balls like, hey, certain things they have to maintain their order, and certain things you're allowed to change. Like for example, if I read from call data, I can put that in whatever order I want, because call data is immutable and it's a read-only operation. So it doesn't matter if I'm reading this section of call data first and then later this section, or in the other way around. So it won't put any thing here. Actually, I'll define this as read control flow. So what this means is that this has to be placed in a certain order relative to things that do write to control flow. So like a jump or like a stop or like a return, these things, they have to be placed in a different order relative to that. Right, so this is probably actually not relevant here, but this is something to keep in mind when you do use balls, is that if you're defining like custom functions, like here, you have to make sure that it respects any dependencies that it might have.
Okay, makes sense. Yeah, I get the limitation now. Okay, so yeah, continuous blocks, all right. If you have a branching statement, you basically jump into how to solve that.
Mm-hmm. Right. So let's skip the beginning and just implement the loop body, because that's kind of the most like tricky part. That's also like the meat of the logic. So we see here that we have the two M stores to basically prepare the call data for the transfer, right? So we want to save the address of the person that we're sending tokens to, and then also the amount. And the way they're loading this is because they assume that these two arrays in call data are going to be at different points, but they're going to have the same size. So the offset between the two values are always going to be the same distance. So this is like the diff that they're calculating. And so we'll have the concept of that too. And then yeah, you load the values from call data, and then you put them into memory to prepare them there, and then you execute the transfer. So we're going to avoid any high-level optimizations for now, just to show that even if you implement things one-to-one, without like being too smart about it, like you will get better gas result in balls or Huff. And then we can look at some high-level optimizations that you could have done in the Yule as well. But yeah, so if you imagine a loop in assembly, the body of a loop, it has to end with the same order of variables as it started, right? Because there's a bunch of variables here that you always have access to, right? Like the address offset, like the diff, etc. Because you're going to rerun the same piece of code again and again. When it ends, it has to leave the stack in the same state where it started. Otherwise, the loop isn't going to work if you call it multiple times, right? So for example, the address offset, if I have this here as a value, I also have to ensure that if it gets updated, it's in the same position, right? So if I have my other variable here, diff, and this I won't change, so I put it like this. This indicates like the stack input, and this indicates the stack output, right? So if I define it this way, then basically what I'm telling balls is that it's going to flip these two at the beginning and end, and that would be wrong, right? Because if you run the loop multiple times now, then next time it'll use the diff as the address offset and the address offset as a diff, and then it'll break things. So you have to ensure that you tell it that you want things to be in the same order, right? So what other variables we also have the token. So let's put this on both ends as well, like the address of the token. And then that's it for now. And actually, as another thing, we can add a variable here on top called repeat. So what this means is that it takes in 3 things from the stack and it'll return 4. And then this value is basically the condition down here, whether to loop again or not. And this will be consumed by Huff to basically do the branching. So it's fine that the stack is different than the input, because this value will be removed in Huff, and then we'll have 3 and 3 again. So yeah, in a loop, you always want to keep the input the same as the output, minus the looping condition. So now let's basically recreate what they did here, right? So we want the address. So for this, we just define a new variable. We call data load. Then we want the amount. We can just call data load again using this offset. Oh, and actually, you can't use diff and balls because diff is a reserved keyword. So diff is not an opcode. It's just the subtraction opcode. But unlike sub, it's commutative. So what this means specifically, this is like a tiny optimization. You rarely need it, but sometimes when you want to compare 2 values in Huff, you can use the subtraction operator, because if they're both the same, it'll give you 0. And if they're different, they'll give you a non-zero value, right? Overflowing or underflowing. So this can be used as the opposite of as an optimization over doing is 0 equals. You can do subtraction in some cases. And if you use diff instead of sub, it basically tells the balls compiler that it's allowed to swap the order of B and A, right? Depending on what's easier. Versus sub, it'll think you're doing a subtraction, so the order of A and B on the stack will be important. So in this case, we'll just do, we'll just call this value relative offset instead of diff. And also, balls doesn't have any indenting on anything, so you can format values of it how you want. So if I want to define my function like this, there's no style guide yet, so kind of make up your own as long as it's readable. You can align things, but I don't know. I think I'll just keep things like this for now. So yeah, we have this, and then we have the relative offset. And you can redefine or re-reference things in these. So the inputs, they define variables, and the outputs are references to variables, right? So you can have the same input and output, which just indicates hey, this value can be used in the function, but it has to still be on the stack at the end, meaning, it'll dupe whenever necessary. Versus if you have some sort of value, for example, if let's say I had some input x that I use in the function, but that's not required in the output, the last time x is used, it'll actually consume it. So that's one thing that Solidity does quite often that leads it to be suboptimal, is that anytime you use a variable, even if it's the last time, it'll always dupe it. And whatever's left over, it'll pop it, right? So this is unnecessary because you're duping once a value that you will, to keep a value on the stack that you'll later pop anyway, right? So Balls is aware of this and will actually ensure that the last time you use a variable it's also gone, right? So then we can actually mstore, and I'm not going to do mstore. Actually, I'll do exactly what they're doing. So I'll mstore the address. At this, I'll mstore the amount at 24, and then we can do the call. So remember, Balls can't do branching, but with this little hack, we basically wrapped the branching code in this API and told Balls about it. So now what we can do is we can just call require not with some value, right? So the success of the call, we can put it in here, right? So now we have our call, and we'll just we'll put the call here. So we'll do gas token, and then we want to pass no value. And instead of 0 as a tiny optimization, I'll pass this value z0. So this is a standard I use everywhere, although you don't have to. Basically, these angled brackets, it looks like the generic, where you put the generics in Rust or something. But here, it defines the so-called macro arguments. So in Huff, macro arguments are arguments that are in line at compile time and don't come from the stack. So here, this comes from the stack, and this is just at compile time will get put in. And Z0 for me always means the opcode. So whether it's return data size or whatever it is, it's some opcode that will always give you 0. I think in this case, because we're doing calls, we can't use return data size. So it'll either be push 0 or it'll be just push 1. 0. So yeah, but I abstracted away with S0, so I don't have to think too much about it, and then I can think about that when I write the huff code. So again, I went from my memory to start at the 0 offset, go to 64, and then 0, 0. So this is the call, and then I require I require not. So this is a require not, so I want to put is 0 in it. I can also define a second function that just says like require and also takes a macro argument like this, and then I'll use that instead, and then I'll put it that way. So now we have our call to the actual token for the transfer. We check its success flag, and then we just want to update the address offset. So we'll say the new address offset is just the previous one. In my language, unlike a lot of languages, you can also put single ticks or like quotes at the end of your variable names. I might remove this in the future if there's strings, but this is because in a lot of conventions, like if you like look at mathematical notation, oftentimes like a tick will denote like some sort of updated or changed value. So I like the idea that you can add one tick or multiple, but it's only valid at the end, right? So you can't put a tick in the middle of your variable name and still have it be valid only at the end of the name.
Interesting syntax.
So yeah, we just update the value.
I've not seen another programming language do this. Did you invent this?
The tick at the end?
Yeah. It's nice. I like it.
No, I think I didn't invent
Obviously,
it.
it's like a derivative or something
this.
from math. But
yeah. I think
fantastic.
Haskell also has this. Yeah, it also lets you do ticks at the end. I think that's also where I was inspired to do it, actually. Now that I remember. But then, yeah, we're basically done with our function, and then we just say that whether the loop should repeat or not is if the address offset is less than the end, and we don't have the end value here, so we can add it here. And now you may be asking why I put things in a certain order. So that's one thing that Balls also can't do for you yet, is order the inputs and outputs in such a way that'll reduce it. It just says here, you just tell it an ordering, and it'll find the cheapest way to achieve that ordering, but it may not necessarily be the best ordering. So the reason I put stuff like token and end and relative offset at the end, it's because these are things you're not modifying, right? And generally my intuition just from experience is that when you're scheduling a loop, it's best to put things you're not going to change deeper in the stack, because it's easy to change things at the very top of the stack because they're already there, right? So for example, if you imagine the stack code later, or we can probably see this, is that you just push 0x20 and then you add, and then the value is changed in place, right? Instead of having to swap the value to the top, change the thing, and then swap it back. But yeah, we'll see. And that's one cool thing about Balls, that it lets you easily check and compare different schedules. So now we wrote the whole function, and let's see if it's valid. So I already installed Balls on my system. So all you need to do is you run the file through it, and then always, when possible, use the -d option. So there's two algorithms it uses for scheduling. One is Dijkstra, which is the D flag, or there's like the default, which is called like the guesser algorithm. So the Dijkstra algorithm, under the hood, it always guarantees you the optimal layout based on the constraints we laid out before, so the minimum amount of swaps. And the guesser algorithm will run faster, but it's not guaranteed to give you the best layout always. Sometimes it'll not be as smart and maybe use a swap when it wasn't necessary. So the only time you want to use the guesser algorithm is when your function is so large that Dijkstra is just not handling it and it's freezing your computer. Because, yeah, it's basically what Dijkstra does is it runs an exhaustive search on all the combinations. And that can get pretty bad if you have like a huge function. So if that's the case, then you want to use other algorithm. But for this small function, Dijkstra will definitely work. And then we'll also add V, which means verbose. So this will just give you some stats about the scheduler. And particularly in this case, we only care about one stat, which is the swap amount. So if we run this now, it'll give us the huff code. Actually, let me run this again so we can isolate it, so we see one screen. And this is the main metric I care about, right? There's a bunch of metrics around the internals of the algorithm, which I should probably hide this away. This is mainly for development. But basically, this is what we care about: the so-called cost of the schedule, or the amount of swaps. And here it only used one, right? Which I think is pretty good. I mean, we can try rearranging things and see if we can get it to be better. So for example, like what happens if we swap these two? And actually, let me change how we're displaying this. It's a bit easier to visually see. But basically, okay, if we rearrange these two, it's the same, right? Different code, but it's the same. What happens if we rearrange this in token? And in Huff, if you were to try these different combinations, you'd kind of do it as you go along, but it'd be much slower, right? So the iteration speed versus writing Huff can be much faster when you're using balls, because you can just go back and forth and see, and then everything is giving me roughly 1. So I'm relatively certain that 1 is the optimal layout. So let's go to the one that was just the simplest to understand that we had before. It was this. Like this, and then, okay, it's still giving me 1. And then this is the Huff code that is special. So you can either copy paste this into a file, or if you want it to be more convenient, you can take your Huff file and you can add a comment that says balls insert start and balls insert end. And then there's an option in the compiler that lets you directly feed this into a Huff file. So I can, and if it finds these comments, it'll be able to insert your code automatically, and then it won't display it here anymore, right? It'll say inserted, and then it's automatically there. So this is great if you want to set up like a build pipeline where you have just like some simple like bash scripts that run balls a bunch of times on different files and pipes them into different Huff files automatically, instead of having to copy paste stuff yourself. And then you have it directly in Huff like this. And if you want the stack comments to be a bit nicer, you can limit the depth, but this may give you like a bad layout. So by default, if you look at the options, the max depth is 1024, like the EVM's max depth. But for example, if you wanted, this will also lead it to schedule faster. You can try lower depth. So for example, 4. Whoops, the help flag is still there. So 4. So in this case, it's impossible to schedule it with 4. It's just like there's no way, because for example, like the call opcode itself needs like 7 parameters. So this is not possible. So we need at least 7, but 7 is still impossible. So we can try 8. But yeah, we have a lot of variables in our stack. So it turns out 11 still works and gives us 1. So now it's a bit tidier. I'm not sure if that's actually less than before or not. I think it's a bit less deep than before. So in this case, we got lucky. But there's some cases where if you constrict the stack depth, it'll still give you an output, but it'll use slightly more swaps, then giving it a bit more room to breathe, right? So there's different like little parameters you can tweak and tune on the compiler. Those are actually the main ones, like the Dijkstra flag, and then also the max depth flag. But yeah, now we have this the loop, the body of our loop, and then if we actually want to define the loop now in Huff, so if we go up here and we just create a macro called like, I don't know, do transfers, right? And then we say take some parameters. So what do we need to start? We need 4, and then let's say just returns 4, right? So basically what we want is also the same inputs here at the beginning. And then we have a label called loop start. We just run the body, and let's also do the Z0 thing over here. And then it'll return what it returns here, right? We can take this, and then now all we have to do to have this loop finished implemented is we do the jump back to the loop start, and now we have a full loop implemented in Huff. And if you imagine how long it would take you to like write all this in Huff and then ensure it's the same layout, and I mean obviously it took a while here because I talked over it, but pretty certain like it would take you more time, and then if you use 2 or 3 swaps, you would have to like actually think about it to convince yourself that okay, maybe I don't have the optimal layout, and then swap things around to find it, and then yeah, we have this. So one small detail, so it might not actually lead to optimizations here, but there's one thing. So as mentioned, balls keeps track of and keeps track of and enforces dependencies. So here we have two M stores, right, that both write to memory. So balls will see this and say, hey, these both write to memory, so we have to maintain the order of these two M stores in case they overlap, right? Because balls is not smart enough yet to recognize that each write only one word and they will never overlap. So if you technically want to see, maybe there's some optimization if I swap these two, one thing you could do is you just swap the two yourself and see if it leads to a better outcome. So in this case, it still gives us just one. But another thing you could do if you want to scale this up and you had like more M stores or whatever, and you know they're independent, what you can do is you can create like a new wrapper function in Huff. So you do you could just call this underscore M store. In this case, I would be careful with this because this is not that safe, but you can call this underscore M store or like unsafe M store if you want to, let's call this unsafe M store, or you can also do lowercase, and then we say it takes two parameters from the stack kind of thing. And then in Huff, we'll just define this as M store. So now balls will see this and think, okay, it has no dependencies. This can always be called in whatever order. And then you can just do unsafe M store, x24 amount, and then like this. And then now it'll swap them around and check for different combinations. And in this case, it'll still give us the same output because we just checked that there's no effect in changing their order. But sometimes this can actually let you do optimizations. And that's why the dependency system here with the reads and the writes is so interesting, is because you can basically define your own dependencies to let balls try and look through more combinations and reorder more things. Like, for example, if you have a reentrancy lock that's in storage, in persistent storage or transient storage, you know that it won't overlap with, like, I don't know, your balance mapping or whatever. But still, if ball sees those together, it'll say, hey, these have to be in a certain order. But instead, you can define this as a separate dependency. Like, you can define your own dependencies here as well, like dependency reentrancy flag. And then you can use this, right? You can say that a certain macro writes this dependency, or you can say that another one like depends on it, meaning it like reads it. And then balls will automatically like keep track of it and say, okay, these things can or they can't be reordered, or they can only be reordered between writes. So for example, like reads, if something is read only, then it can be reordered, but only in between writes, right? So stuff like that, that'll take care for you. That can help you optimize your code even more in a more like automatic way. But yeah, now we have the transfer loop body up here, and now we want to implement the rest of the function, right? So we have the start. So let's implement a macro that'll give us the start and the setup, right? So let's just define one big function here. Let's call it setup, or let's call it start, and let's open up the code here so we see it. So one thing is we want to check the lengths. So we'll start with an empty stack, right? Because we assume this is just somehow called, and then it'll return some values. So one thing is we want to compare the lengths of the arrays. So here we don't have solidity to help us and tell us where the offsets are, so we kind of have to manually see them. So this is, we'll start at 0, this will start 4, and then this will be, so this is the 0 word, this is 1, this is 2, and then the length will start afterwards. So if we think about the call data layout, let's just draw this up real quick here. We have our selector, which is 4 bytes, and then we have the token. Then we have the addresses, the relative offset, right, because it's call data encoded, and then we have the amounts. Then we have the total amount, and then the arrays will actually start. So the addresses array will be first. So here, this should be addresses dot length, and then we'll have the elements here for addresses, and then we'll have so this can be times n, and then we'll have the amounts dot length and elements times n. So we don't necessarily know the start, so we want the relative offset. So let's do address relative offset, and we'll load it from 24, and then we want the amounts relative offset, and I think you need to do plus 4 to get it, if I remember correctly, because it's relative to the entire call data, but we can debug that later. So yeah, so now if we want the actual start, so we want the address start, it's the address relative offset plus 4. I don't know, Shaf, if you remember the exact offsets. Well, we can check this in a second. So here.
Yeah, it would be interesting to see actually if how to debug this, if it needs debugging.
Yeah, I'll definitely show that. That will we'll probably almost likely have to debug it because there's always like some little detail that's off. And for that, you just use the Foundry debugger, which is very helpful. You just open the Foundry debugger on one screen, have the your code in the other screen, and you can kind of like follow and match them up and see what's happening where. So here we're just manually decoding the call data. That's just the cool thing about a high-level language like Solidity, is that all these little like off by one errors or decodings, like it'll do automatically for you. So you have to do them yourself in this case. So if we want the address length, now we can finally read it by doing the address start, if we got it right, and then the amounts len, and then we'll do the amount start. Or let's call this actually offset, as you would in Solidity. So address offset, and there's no LSP yet either, so you have to trade off if you want the gas or if you want the developer experience. You have to see. But now we can actually check. We want to check that there's actually not a difference between the address length and amounts length. So this is where the diff I mentioned comes in handy. So this is just abstraction, right? So here, if they're equal, it will be result in 0, and then this will not revert. But if it's if there's any difference, then the subtraction will either underflow or overflow to a value that's not 0, and then it will revert. But to tell balls that this can be rearranged, you tell a diff, and then it might put the first one first or second.
Okay. Actually, because you mentioned an LSP, the syntax highlighting, I guess, is from Huff. You didn't write any syntax highlighting for bonds?
No, so I did. This is using tree sitter, and it's not part of the main tree sitter like repo in NeoVim. So in NeoVim, there's like this plugin called tree sitter that does syntax highlighting and auto-completion and indentation for different languages. It's like the common like standard like API. And I implemented the syntax there for it. But as far as I know, if it's not part of like the main repo, and balls is, I don't think a real enough language yet to be in there. I don't think I can get it added there. So for now, if you want to install the syntax highlighting, you have to do so manually. I think the repo is balls tree sitter.
But that's awesome, man. I thought you were just reusing the Huff one, but it's awesome that you wrote one yourself. It's pretty dope.
I don't know, maybe ball sitter? Okay, I'll link the repo afterwards. I don't remember where it was, but yeah.
Okay.
Yeah, because it's not exactly Huff syntax. You know, it's almost Rust-like in a lot of ways. But yeah, so now we check the length as we did here. So all this code here, all these lines, they're just basically what Solidity does implicitly for you. And then we can also, let's load the token and the total amount. So the token is just call data load 04, and then total amount is just call data load there. And we know this from here, right? So it's 0, 1, 2, 3. So 3 times 20 is 60, and then plus 4. I mean, this is not actually 60. This is 96 because it's hexadecimal, but that's why I like writing hexadecimal in this case, because it lets you do the offsets more easily. And actually, that's one small but cool thing in balls, is that it'll let you write either decimal numbers or hexadecimal numbers, where in Huff you're forced to always write hexadecimal. So that's also kind of like a nice quality of life feature here. So based on the situation and what's more readable to you, you can use one or the other. And then, yeah, we can actually start preparing the stuff in memory. So let's do mstore z0, and then let's do this value. So we do this, and then in this case we have to do the padding manually because it won't be inserted for us. So I think it's 56 zeros. And that's the cool thing about Vim is I can just type 56 on my keyboard and then 0, and then it'll automatically get added. And if we check the total length, it's 64. So that's correct. And now we can do 4 and do the caller, the address, just like it did. So it's, in this case, it's actually almost identical to the UL, and then the total amount. And then we also do the call. So we do the require, and then we call gas token z0 z0 064 z0. Right. So like this, we have this control flow if in here without actually having to interrupt our balls function and hop to huff. We can do it all in balls. And then after we've called this, we can do the mstore for this selector. So let's do that again. 56 0 in here. And then we want to calculate the start of the arrays and the differences. So let's do that too. So the end of the addresses array will be, so the end will be a word because that's where the length is stored. So the that plus the offset plus the amount of addresses times 32. So 32 is the power of 2, so we can actually use bit shifting here because 32 is 2 to the power of 5. And in the EVM, bit shifting is slightly cheaper than multiplication. So we can do that here. It's actually exactly what they do here as well. So we do the length, and then the distance, or like the relative offset between the two is that offset minus the other offset, I think. Yeah. So we'll do, so in this case we want to use sub, not diff, because we wouldn't want the compiler to rearrange things for us. So here we want to use the amounts offset. Oh wait, it subtracts the, okay. Oh yeah, because the addresses are earlier than the amounts. All right, so let's do the address offset and the amount offset here. And now we want to say that start should return all these values in the order we need it for the array. So we want the address offset first. And this is actually the offset where we start reading, not the offset of the array. So actually we need, so we can redefine, the balls lets you redefine variables. So you can do address offset is equal to add address offset 0x20. You can do that. So our first variable is address offset, then we have the relative offset, then we have the token and the end. And now if we let balls compile all this, let's remove the max depth just in case. Oh, it's actually taking a while. So now it's running and it's taking quite long. So this is a case where we might need to use Dijkstra. So if we look at activity monitor and we check the CPU and memory usage, we'll see that it starts to skyrocket and it might not actually finish. So if we look at balls, it's using all my CPU, and if we look at memory, yeah, it's already at 20 gigs of RAM because it's just like searching all the combinations, and it's going up. So before my computer crashes, let me stop that, and let me see if we can reduce. We can reduce this. Yeah, because what it does is it looks at all the possibilities, right? So if we remove Dijkstra and we just let it run heuristically, it's gonna finish really fast, right? So it's still found for transfer body a schedule with 1, and for the start it found one with 2. But now because we didn't use Dijkstra, we don't know if 2 is actually technically the most optimal, right? It's just kind of like a a guess, but it completed quite quickly. And honestly, I'm happy with 2. I think we'll almost definitely beat the assembly anyway. But yeah, if you're really a perfectionist, then you might have to tweak it a bit for it to actually be able to run fully. One thing that helps a lot actually is capping the depth. So if we cap the depth to maybe 12, I'm not sure if that's enough for... Actually, let's look at the output. So it did go quite deep. And actually, I dislike that it puts the whole thing in here, the padded version. So what you can also do in balls is you can define a constant that comes from Huff. So you can do constant transfer from, and then constant transfer. And then I'll just use these instead. And then this will make the code cleaner, but I'll have to define them in Huff, but that's not a problem. So let's regenerate this again. And now the stack is a bit cleaner, but yeah, this is going really deep. So that's why it takes so long, is because, yeah, it looks through all the combinations, and when your stack is getting this deep, it can cause some problems. So if we restrict the depth to, like, let's restrict this to 15, and then let's try Dijkstra again, and maybe it'll actually work this time. But it might need like a few seconds to run, or maybe in minutes.
Okay. I'm just worried for your RAM, man. Just
yeah, the RAM. Yeah, maybe that isn't finishing that fast. Let's try 12. Let's see where we go with 12. 12 should actually be feasible, I think. Let's see what the RAM is doing. Memory pressure. Oh, something is going up. Something is going up. Yeah, I don't think my computer is liking this too much. Okay, let's stick to not Dijkstra for now. And we'll just have to live with this result. But, 2 is probably the best. And we can still limit the stack depth to make it look a bit cleaner, potentially. Oh, so 13, it still finds it. 12, 11. Ah, look. So now we found a weird situation where with 12, it finds 1 for the body. But if we do 11, it finds 2, right? So you have to be careful when you limit the depth. But if we know that 12, it still finds something, then maybe we can try Dijkstra on 12 and see what it gives us. But it might be too slow. Also, this is a live stream, so I don't want to take forever. But yeah, if you have time and you have the resources, you can... But the issue with this algorithm as well is that it's exponential, right? So it being a little bit longer can actually indicate that it'll run much, much longer. So yeah, let's say we're happy with the result, and we'll do this so it looks a bit cleaner. So we have our code. And yeah, all automatically generated. Imagine you have to write all this by hand in Huff would be kind of a pain, I'd imagine. So yeah, let's define our constants now. This was this padded. And then we also need the transfer constant, which was this. So now we have these constants. And now we just have to string these methods together, literally. So what we do is we have the output here. And if you look at the output here, this is exactly what we take here as the input. So actually, let's define this as our underscore main function. And let's define our main. So usually I use return data size as the push 0 opcode because it's backwards compatible. But in this case, we could check that call value is 0 and then use call value. But I think in this case, it's just simpler to use actual 0 and it'll just push 1. But we'll be happy with that. And yeah, so we do, so instead of taking 4 and returning 4, let's do 0, 0. And at the end, we will just stop. So stop doesn't care if there's stuff left on the stack. The EVM will just be like, okay, you're stopping now. We don't care what's on the stack. And then start up here, which will give us all our values that we need. So one little optimization I made that Solidity is not able to make is the loop, right? So if you imagine the loop and how it's implemented, is that you have these conditions. You have this condition at the end, and it will check this condition if it needs to jump away, right, the break, and then it has another jump to the top. Instead here, I have a single jump at the end that will jump to the top if it needs to loop again. But the issue is, what if the loop is done on the first iteration, right? So in this case, we need a way to stop early. We can have a label here that jumps straight to the stop, and we can just have an extra check here. So I could implement this check in Huff, which would look like comparing the address offset to the end and seeing if they're equal. So this would be dupe 1 and then dupe 5, I think. And then you would have this layout. Address offset end. And then you could compare them and then skip to the no loop, right? And then you would have this logic here. And then you have one extra branch the first time, but then it's cheaper every subsequent time, which is pretty nice. And even this condition, I would often write it in balls because it just seems a bit cleaner, and thinking about the dupes and making sure they're all correct just is kind of tricky sometimes. So just I can implement something like this called like skip loop. It takes this and then returns this. Oh no, we want this version. Yeah, because in Huff I like to use the reverse stack ordering. So the deepest end of the stack is to the left, and balls uses the other way around. So the deepest end of the stack is to the right, which most people use. So in this context, it's kind of confusing that you have to flip other things, but most people write it deep on the right and top to the left. So it's fine here. So we have our stack here, and then we add the value here, whether we should skip, and we can calculate this very easily by just saying skip is equal to if the address offset is equal to the end. And it's basically the same, but if we compile this, it'll give us 0, which is good. And if we look at what Huff gave us for this function, it's super simple, right? It's almost the same instructions, it's just flip the 2 around. But it just gives me that extra bit of safety that, okay, I did the dupes correctly, everything is fine. So I just replace this with skip loop, and then I know whether I should skip, and then I have this, and then this should be the full function implemented. Now we don't have the dispatcher to check the selector at the top or whatever, but we'll skip that for now. And now let's try and test the contract. So let's first see if it compiles. So I'm going to use the other Huff compiler for this. Although it should also work with the other one. Let's try the real one. Yeah, we have to actually define our require and no require. So for the no require, I'm going to put a global revert here at the end and do 0, 0 revert. And then I'm going to define a macro called require not that takes 1, returns 0, and all it does is it will jump to the revert if the value is non-zero, and then the require is very simple. It just takes the value and then so no revert here, and then it doesn't revert if the value is non-zero, right? I will not put the stack comments here because it's relatively simple. I just want to see if this works. Okay, so compiles in both Huffs, and then let's actually get the runtime code. All right, nice. So let's actually test if this works.
Philogy, question.
Mm-hmm. Yes.
What's that other Huff compiler? I've never seen this before. Huffy.
So the other Huff compiler is the Huff compiler I rewrote in Python that doesn't have all the features of the original Huff, but is heavily simplified and lets me modify it quite easily. Because if you ask the original Huff authors about the Rust Huff implementation, they will also say that it was one of their first Rust projects back when they were learning Rust, and it's just in a lot of areas it's overly complicated, and I just wanted to have a nice overview of the compiler and optimize certain things. in the compilation. So for example, my Huff compiler will actually let you do 1 byte jump labels instead of 2 byte. Although I think they added that to the other one recently as well. But there's just like some small details that are slightly improved. Some details that are worse. So yeah, I just like to use it because I wrote it and I'm
Yeah.
familiar with it. But yeah, there's not
Yeah,
a
sorry.
there's not a huge
Actually,
difference.
this was a super dumb question. I just looked at the repo and I did like a small PR on the repository. So I remember now. I remember now. Okay, so yeah, it's a Python implementation of the Huff compiler. Nice.
Exactly. So let's actually test this. Test airdrop.t.sol, and then let's actually get an ERC20 token in here. So let's install our favorite library, which is Solady. All right, awesome. So now we have access, so we can write a mock token. So let's do mock ERC20 sol, and then it's ERC20, and we'll get the something is wrong with keyboard. Okay, ERC20 from Solady source tokens ERC20, I think. Let's see if that compiles. Maybe just directly like this. All right, so we have to implement name and symbol. Let's do that. Like this, and we have to pure override so we don't get any warnings. All right, so does that compile? All right, now we need to actually write our test. So, oh, and let's write a mint function here so we can actually give ourselves some tokens. So, function mint to amount external. All right, and then we have our airdrop test. So we actually want to be able to get the code in here. So let's do deploy Huff, and we'll get the address of the airdrop contract. So first we want to get the bytecode, or let's call this the init code, and this will be using the VM FFI cheat code. So this lets you interact with CLIs outside of that are on your system, but not there. And then I'll do an array of string arguments here. So string memory args, and then args 0 Huffy. Then the first argument is we want the deploy code, and then we want to do source airdrop.huff. All right, and then let's pass in the arguments here, and then we actually need to deploy them. There's an error from my editor. I don't know why I get that. And then airdrop create, and then we unload. All very classic, and then we can actually test. So we need an interface for this. We'll just do a pretend interface. Airdrop, and then let's do the same interface. Actually, we can just literally take that contract. So let's do airdrop from source airdrop, and then now we have the Huff version, and we'll just say Huff is, we'll just wrap this version. So now let's write the actual test. Airdrop too many, and then we'll create our token, Here token. So let's create our sender. Our sender will receive some tokens. And then our sender wants to send a bunch of people some stuff. So let's do, we'll send our friends some tokens. And then let's do like this. And then they'll all get some amount. And then let's do, I don't know, let's do 3 each. So I'm using Forge FMT to make everything look nice. And then the total is 9. So now let's do VM. Let's do start prank the sender. They want to approve our contract. Let's do a practically infinite allowance, and then we'll actually call our contract. So we'll do a huff. What was the function called? Airdrop ERC20. It will be fortunate and unfortunate if this works on the first time, because then I can't show you guys how I debug this. But I don't think it'll work on the first time. These things never do. And the total is just 9. And then let's see if it works. So I have so many terminals open. Let's close some. Let's close this too. Let's use this one. All right, Forge T. We gotta enable FFI. Let's do 4 V's in case it succeeds, so we can see the trace. And then it doesn't compile. And then airdrop. Airdrop. In airdrop. Airdrop. Oh, I call this airdrop. Okay. Airdrop. Okay. And compiling. Reverting. Okay. So, oh, not activated. Okay, so this happens because I think it used push 0 and we don't have Shanghai enabled. So let's do, I think, EVM version Shanghai. And then that should be good. Okay, so it looks like it actually worked. Wait, but who is it transferring
I
to?
didn't expect that.
Yeah, I also did not expect that. So wait, we have 4 transfers. We're transferring to friend 1, friend 2, friend 3. And then we are, who's transferring? From the contract to somebody else, we're transferring 3 tokens. Okay, something weird is happening here. It's being called 4th time. With 0? Oh, it looks like it ran one. It looks like it, yeah, it looks like it ran one time too many. Maybe I started the offset too far back. So let's look at our balls code. And the start. So the reason I suspect that we're starting too far back is because it's running one iteration over and it's giving us an amount of 3, which looks like the length of our array. And then 0 is probably just out of bounds. So it looks like it just runs 3 times and then runs again. But the first few are correct. So maybe the end offset is not correct.
It's actually not an amount of 3. It's The to address is 3. The amount is
The
0.
to address 3. Yeah. Good point. Good point.
Yeah.
So our end, we're setting our end to be the offset plus the length plus 20. And then difference is the amounts offset. Okay, let's see what's going on. I guess we need to debug this then. So let's do. So for this, we just do dash debug with the name of our test method, test airdrop to many, and then we'll enter the Foundry debugger. So it will start from the test, and we want to skip all the calls and go to the call that our contract has, right? So we make a call, we create the token, we call make address, we call mint, whatever. So let's go to the very end, and let's go back. So let's go back one call to the stop prank. And then let's go back. So unknown contract. This looks like it's our contract. Okay. So this is the point where it ends the loop. So let's go back. Oh yeah, because this is when it calls into the token. So it calls 4 times. So let's do 1, 2, 3, 4, 5, 6. So again. Okay, here. I think we're almost at the start. So that's also, actually, one way we could simplify this a lot is there's this cheat code that is VM breakpoint, and then you can add like a character. And then if you enter the debugger, you can actually jump straight to the breakpoint. So I can now do C to the breakpoint, and then my next call should be into the contract. All right, so now we're in the contract. Great. So let's split our screen. Oh, okay, let me quit the debugger and start it again. A terminal size too small. Okay, never mind. Then we have to do it full screen and just switch back and forth. So let's jump to our breakpoint and go into the contract. So we have our values here. It's calculating. Let's see the call data. So we have the call data here, so we see what we have. So we see 80 is the start of our array. Okay, so we're loading some stuff is happening, and then we're looking for the subtraction opcode because that gives us the difference, or actually right before the jump. Oh no, that's the comparison, I think. So that's the, so that was the call. I think that was the call to the function. So what we're looking for is, it looks like the end is badly calculated, the end offset here. So we're looking for that. Okay, that was the call. Oh, then we have another one. Equal. What are all these comparisons? We have a require, and we have a require. Are we even in our contract right now? Let's call it load. Gas. Yeah, this was like solidity contract. Okay, I'm a bit lost. So it can be hard to debug occasionally when we're doing this. So if we look at our Huff code, if we look at our loop, at the very end we have a greater than. And if we open a new terminal and we look at where that greater than is, so we actually compile the runtime code, and the greater than right before the jump I, right? Perfect, it's right there. So now in the debugger we can look for that. So B4. Okay. Yeah, because when I skip to the next jump, it okay. Oh, did that jump right to the end? Okay, never mind. Let's do C. Okay, so we're in here. Okay, back to the start. We add 20. So when do we add 20 in our contract? We add 20 to the final offset and here. So it has to be end. Are we already calculating end at this point? So we call data load 0x04, which is the token. We push these values, we load the relative offset, and then we add 4. Right. We add 4 to the relative offset, which gives us the address offset. And then we push 20. And then to this value, we're calculating the final address offset. Okay. Okay, this is the final address offset. All right. Yeah, so this looks weird because we calculate the final address offset right at the end of our function, but it does it right at the top, right? So that's just balls doing its magic and rearranging things. And then actually what's much easier to follow than the balls code in this case, when you're debugging, is the actual Huff code. So where are we? We're here, the second push 4. I think we're here, actually the third push 4 technically, here. So yeah, we have the address length. We have 044, then we read the amounts relative offset, right? Then we compute. So we want to find where we compute the end. Where do we compute the end? The end is computed right here. So we're almost there. Right before the swap. Okay, let's do up to the swap. 7. So we shift left 20, and then we add it to the amounts offset. Oh, sorry, the addresses offset. Right, it's the addresses offset. Yeah, addresses offset. And then we add another 20 for 104. So if I scroll down the call data to see where that is, the end is right here. So that seems to be correct. That seems to be the correct end. And then it's swapped away. So maybe something is wrong with our loop. So we mstore, we call data load, we do a bunch of stuff. We mstore, and then we call. Can we get to the end of this call? All right. We recall, we have, so this is the actual ERC20 token transfer. So this is what's happening in the background of the VM, you know, when you do a transfer, there's a bunch of stuff that happens. And then, okay, now we're back. We store the new selector. We jump based on the success. And then we jump based on some different values. If we go back here, yeah, this is the very end. So where we jump once and then we jump another time. And now we're out of this code, right? Now we are in the skip loop portion, right? So if you remember, skip loop is just duping the values, comparing them, they're not equal, so we're not going to jump to the end. And now we know that we have to execute one iteration, right? So let's jump to the next jump using S. Is there a way to jump over this? Okay, let's just go through it. And all right, whoops, a bit fast. So we returned, we jumped over this. So now we compare this, it's still not there. Oh, I see. I think I see the error. Okay, so what we saw there is that the two values get compared, but the value that gets compared is the wrong one, right? It's the counter, but it hasn't been updated yet. So if we look at our function balls and we see if it repeats, look, that's the error. You see, so we're comparing end with address offset, but it's not been updated yet. So it's the value we had at the beginning of the loop, not the end. So I have actually had this happen to me quite a few times because of this little tick here, because it looks clean, but it's also very easy to confuse the two. Instead of like update it or something, or instead of just like replacing it, you call it something slightly different. So I think I'll actually remove that in the future because it is confusing. But yeah, I think now if we rerun it, oh no, sorry, I have to recompile the balls. And then now if we rerun it, it should be, yep, now it's only 3 transfers. All right, there we go. So now if we assess the gas, let's do the gas report. Approve mint. It doesn't do a gas report for the Huff contract. Okay, we might have to just do 4 Vs and isolate. Then we can also get the gas cost. So if we look here, we spent 113,000. And now if we swap it out for the Solidity version, let's do that real quick. So let's do instead, let's just keep calling it Huff, although it's not Huff. We'll do an actual airdrop contract. And then if we rerun this and see what the value is, so instead of 113,000, it's also 113,000. So the difference is smaller than I thought. The difference is 655 gas. So it's not huge. All right. In this case, it's not huge. It's about, what is that? That's about 220 gas per loop iteration. And when your main transfers already cost 20,000, it's like 1%-ish gain per iteration, right? Yeah. Not huge. I mean, now we can start to make like high-level optimizations. So, for example, one thing we can do.
Question.
Yep.
What is isolate doing in the forge command?
Yeah. So isolate is this new mode they introduced that changes how they compute gas. So it makes it like as if it were actually running on mainnet, versus the warming and cooling being different, right? So without isolate, you'll see it's actually a bit lower because it'll treat the entire test as one transaction versus treating every call as its own transaction.
Okay. That's a cool feature.
But yeah, I guess that's a demo of Vol. So you see the gains are not huge, but if you need those gains, and they can be much larger, like I showed an example where I compared Huff code to Solidity for adding numbers. and there was there the gains per loop were actually smaller, but they added up more quickly because it was adding numbers. So here, like if you're airdropping 100 people, that's 100 times 200 gas. That's yeah, it's already 20,000 gas. And I mean, this has nothing to do with balls anymore, but there's things we could optimize that are more higher level, you know, that don't require this low level optimization. One thing, for instance, would be that there's a require in every loop, right? There's some branching in every loop. Instead, what we could do is we could just track like a global error value, right? Or a global like success value. Actually, instead, so what we could do is based on the success flag, we would do an mstore8 to the byte in memory that is in accordance with this flag, and we would override it with 0. Right, and then at the very end, what we would do is we would check whether the 1 was ever overwritten. This requires us to change some. Actually, okay, this live stream is about balls. Let's stay at low level optimizations for now. Yeah, I mean, there's not any more low level optimizations to make here. So yeah, I guess that was the demo. If you're writing low level code, especially Huff, use balls because it'll auto generate a lot of code for you. And if you ever want to make a higher level of, actually, I think this is actually a good demo of balls. So let's say we want to make a high level change to our low level code, right, without rewriting too much code. So we want to rearrange the memory layout such that so instead of having these left padded, we'll just have them to the right, and we'll change our memory offsets. So we'll do, instead of 04, we'll do 20, and then we'll do 40, 60. And then here, instead we'll have this start at 1C. And then similarly for transfer, we'll have, whoops, let me swap these again because it didn't make a difference. We'll have these at 20, 40, and then we'll have this also 1C. And actually we don't need 64, we just need 44. Oh, actually that might have been why mine was costing more. Okay, so this change itself shouldn't be, shouldn't make that big of a difference. It actually shouldn't make any difference. But here, let's remove the padding. And let's rerun our code. So, all right, we're going a bit over with the live stream, aren't we?
Just a little bit. Like I have to sleep in like half an hour, but we're okay. We're okay.
Okay. Good. I think this will be the final thing I show. But yeah, okay. So we made a minor change, and look, the Huff code updated automatically. We didn't have to worry about that. Although I think for that change specifically, we could have done it easily if it were just Huff as well. But now let's make a bigger change, right? So now we have, so we're overriding. Let's make the change that we don't check the success on every loop, but we make it overwrite the value in memory. So we'll have it write 0 to the byte with offset success. So what this means is that if it's always successful, it'll always be 1, and it'll always only overwrite the byte at 1. But if it's ever failure, it'll overwrite the 0 byte in memory with 0. So that means that if at the start we set the 0 byte to 1, a non-zero value, and then check it at the end, this will be 0 if it failed at any time. So it's the same as checking every loop, except that in the revert case it's more expensive, right? Because here, let's say it reverted on iteration 3, then we would already stop at iteration 3. But here, if it reverts on iteration 3, it'll keep calling 7 times and then just check at the end. But most of the times you're not going to revert, and you should try and optimize for that case. So let's do that here. So at the end, let's add a new function now, which is check flag, which basically says that we want to require that the 0 byte from offset 0 is non-zero, which is a lot of zeros in a sentence. And then this check flag, we just have to compile it. Look, transfer body actually now has 0 swaps because of our change, right? And that was discovered automatically. Like we didn't have to do anything for that, and realized, hey, now that you move things around, we actually no longer need a swap for that function, which is a cool realization. And then now we can just put in our code at the end, before the stop, let's put a check flag. And actually we can put this before here. So if the loop is skipped, we know that it couldn't have failed because there were no transfers. Actually, we'll also do the same pattern for the first transfer. So let's do that. No, it won't work. Okay, let's keep it like this for now. So now let's see that our code still works. No, it does not work. Let me compile this and see why it's failing. Yeah, check flag needs the 0 argument. I always forget that. So let's run it now. So still gives it 3 transfers, and now it's even cheaper. Let's compare it with how much it cost before. So before it cost 224, and now it's 220. So it dropped by 4 gas. But I think the savings will be larger the more iterations you have, because we have quite a few iterations. Let's actually pump up the numbers to make it a bit larger. Let's make it 10. 10, 10, and then 3, 4, 5, 8, 9, and then we can copy this over here. All right, and then we can do the same here. And the total is now 30. Let's see if this still works. So current version for 30 costs, looks like it worked, costs 291K. So let's make some further optimizations. Now, in the start, we also unnecessarily check a couple times. So we also want to ideally use this system. So what we can do is we can say that what we store from the start is the result of this. So if they're equal, it will be 1 and store 1. Otherwise, it'll be false from the start, and then it will revert at the end. Here, but the problem is now we have this mstore that overwrites that. So let's put it before. But this mstore will also overwrite that. So what we can do is another optimization I wanted to make is we can have the, let's say, packed selectors. So like this, we can write both selectors into memory with one mstore. So let's do that here. And now this will work. But now we have to slightly change our offsets. So we can remove this mstore completely. And this will still work. But now these will be at a slightly different location. So this will be 1C and 3C, and this will be at 1.8. Wait, does that 12 minus 4 is 8? Yeah, that should be correct. So let me explain what we're doing here. So if we look at this, we can put it into one constant. And what happens is now the packed selectors. So what happens is when they get mstored now, they'll get mstored together and they'll be right next to each other, right? So from offset 0x18 to 1C, it'll be this. And then from 1C to 0x20, it'll be this. And this is written before that. So that works. And then we can do the similar thing as we did before, where we store success in a thing here, and then we do mstore8 success z0. So it's overwritten if it's ever false. And then if we rerun that, so let's compile the balls. Let's compile the huff to see that it works, and then let's run the solidity test. And then it works. And now we dropped from what was before, 291,303 down to 207. So yeah, the gains are getting small. The gains are getting very small, I must say. But they're still gains. They're still gains. And I mean, okay, this is super tiny optimization, but yeah, we can change this to M size as well. What else can we do quickly before you have to leave? I think this is more or less as good as it'll get. As good as it'll get for now. So let's do that here. Oh no, wait, we need to run balls, and then we need to run isolate. So if we compare this one, 291,267, to the one before, 7-0. So we save 3 gas, so more savings. But the main point of this demonstration is that if you're writing low-level code, balls makes it much easier to read, much easier to update, much easier to maintain, and also in a lot of cases will optimize the swaps for you automatically, which is a big part of writing Huff. So yeah, I hope this was helpful. Don't want to keep you from bed, and hope the few people watching understood, and hopefully also enjoyed the broadcast.
Awesome, man. I think that's a great summary. It's a pretty interesting tool. So yeah, guys, thanks for tuning in. I have to go to bed. I'm in Germany. It's like 10:30. That's very late for Germans. So yeah, thank you for tuning in, guys. Philogy, thanks for taking the time. This was a lot of fun, man. It would be cool if you could put the repository on GitHub or something, if people are interested in it, that so they can take a look at what you wrote on the live stream. I'm gonna put the balls repository, the Huffy repository, and all the other relevant stuff in the description down below. Philogy, thanks again for taking the time, man. This was fun.
Yeah, fun. This was fun for me too, and thanks for giving me the opportunity to show people my balls. And glad to do it anytime.
Yeah, you had to do it. You had to do it.
I had to do it.
Nice. Awesome, guys.
All right.
Thanks for tuning in. And
Wait, where should I drop the links? Should I drop it in the